Let's take a look at the base 2 numbering system, better known as binary. In this system, we've got 2 possible digits in our character set, 0 or 1. So how is it that we're able to represent numbers bigger than 0 or 1 in binary? Well, the same way that we're able to represent numbers bigger than 0 through 9 in the decimal system. We'll combine many together and have a system for how do we think about the next largest number and the next largest number that we want to represent. Specifically in this video, we'll be looking at unsigned base 2, meaning we're not going to be able to represent negative numbers yet or fractional numbers yet. We're looking only at integers and only at positive ones, and then we can expand upon this knowledge later to understand how we might represent negative numbers or signed values, as well as a different system for representing a floating point system where we've got decimal values. So we're going to be thinking in this video in terms of a nibble, and a nibble is made up of 4 bits or 4 places where we can have either a 0 or a 1. And we think of each of these placeholders, we're going to see it's a little bit different than base 10, where we have the ones place, the tens place, so on. But I'm indexing these places in this system to indicate that 0 is our low order bit, meaning this is the least significant bit in our number that we're going to represent, whereas 3 is going to be the most significant bit. And I would encourage you to try pausing the video here and writing down all combinations of these bits that you can imagine. And if you can try and do that in a systematic way, starting from an initial organization where starting from 0, 0, 0, 1, oops, sorry, 0, 0, 0, 0 is what I meant to start with, as your very first pattern, or bit pattern we would call it. And I might even just number this as 0, and then we can count this off as 1. And then 0, 0, 0, 1 would be another alternative combination of bits. I want you to try thinking of other combinations and see if you can do it in a somewhat systematic way. And as you do that, try numbering them. And we'll see that there's a specific systematic way that we might do this, but go ahead and give it a shot on your own. I think it's instructional to try this without necessarily knowing exactly how to do it yet. All right, so the first problem you were probably faced with is, what do you do next? Well, the most intuitive thing to do next might be to do 1, 1 here. And that's another valid pattern. But we're going to see that if we're thinking of this in terms of a numbering system, and I said that, okay, well, let's actually think in base 10 for a second. And I gave you a number like 0, 9, and I told you what's the next number. Well, you might form a combination like 19, but you know that that's not necessarily how we count up by 1 in decimal. There's this rule that applies when you're adding 1 to some given placeholder that comes before you. So in this case, we would actually reset the digit that came before us. And what we're doing is we're carrying. We can't go any higher than 9, so we carry it forward. Well, let's carry on with a similar idea here. So if we're trying to add 1 to this line, we know that we're adding 1, and now we've got to carry 1. We can't fit another digit in this first position. So we're going to reset that to 0 and then make this next position 1. Right? And so that's how we would count up by 1, and this would be the second ordinal in our binary system. Right? So notice if we took 1 and did 1 plus 1 and put them on top of each other. In fact, let's go through that really quickly. I'm going to change colors for this. Actually, I'm going to leave that pattern there and just try and illustrate this with an example to the side here, or up to the side here. So I'm going to make myself a little bit smaller and say, okay, how do we add 0, 0, 0, 1 and 0, 0, 0, 1? Well, if we're trying to add these things, we need to carry the 1, right? So we wind up having an extra 1 here, and we can't do that. So we're going to see that that carries over, and we're increasing the next placeholder by 1. So that must mean that this is the 1's position, and this is going to be the 2's position, right? Because if we have 0, 0, 1, 0, that we're representing a quantity of 2. And we'll look at a specific formula for this using a summation like we did with base 10 very shortly. But let's keep going here. So what's the next? If we wanted to add 1 to this bit pattern, well, if we can imagine these two numbers added together, well, we can say, okay, 1 here, 0 plus 1 is 1, 0, 0, 0, 0. Okay, and that might be how we represent 3. And notice that in the 1's position, we have a 1, and in the 2's position, we have a 1. So we have 2 plus 1, or 3. Well, we've got a more interesting carry that happens when we try and add 1 2, 3, right? It turns out we are out of places. We're going to have to carry from here. We're going to have to carry from here. And each time we're carrying forward, we're going to need to reset that placeholder back to 0, right? So this would be 0, 1, 0, 0. And that would be how we represent 4. Right? And so this must be the third index here, or index 2, if we're starting from 0, must correspond to the 4's placeholder. So we're getting the sense that we're increasing each placeholder by powers of 2, right? Whereas in base 10, you have the 10s, the 1s, the 10s, the hundreds places. Well, here we have the 1s, 2s, 4s, 8s, 16s places, where each time we increase our placeholder, we're doubling, or we're increasing our value for that by a power of 10. Well, how do we count up from here? Well, we add a 1 here, 0, 1, 0. That would be the 5th value we can represent. And we can keep doing this, right? So we're going to have to carry that 1 again. So we'd have 0, 1, 1, 0, 4, 6. And notice here, if this is the 2's position, that's 2. Plus, if this is the 4's position, plus 4. 4 plus 2 is what gives us 6. Right? We'll go a few more steps here. I'm not going to go through all 16 possible variations, but I would encourage you to try. So we can now add 1 here by saying, okay, 1, 1, 1 for 7. And when we get to 8, notice we're going to have 3 carries that we have to do. So if we added 1 to this number, we would have to add 1 here, carry it, carry it, carry it. So 8 is going to be 1, 0, 0, 0. And hopefully you get the sense of this pattern. We could continue on from here, and if we took, let me highlight this range. If we took the numbers in this exact same pattern and in this exact same order, and just put a 1 in front of them for what comes after this, we would be counting up 9, 10, 11, 12, because that 8th position, or the 8th spot, has a value of 1, and then whatever comes in the 3 positions after it would be added onto that. Right? So I would encourage you to try writing the values 9 through 15 and reason through why 15 is the largest value you can represent in a nibble, and be sure that you're comfortable with that, and then we'll continue on. So just like we saw with base 10, there's 2 digits in base 2, 0 and 1. And as we just discussed, we think of the high order place as the leftmost in a binary sequence of bits when we're thinking about unsigned integer representations, right? So this one is in the 4's position, right? This one is in the 2's position, and this one is in the 1's position. So each time we move a placeholder over in base 2, we're increasing by a power of 2, whereas in base 10, each time you move a placeholder, you're increasing by a power of 10. And we looked at how the carry works out. If you wanted to check over your work for how the sequence of values of bits in a nibble increases from 9 to 15, you can see that over here on the right-hand part of this slide. Right? So let's do what we did with decimal numbers and look at a brief formalization of how we can actually write a summation formula that represents the integer we can compute using a bit field where our bits are going to make up a vector, just like we saw with a decimal number. So we're going to use B to represent a sequence of bits, 0s and 1s. We're going to index those bits from W-1, where W is the width of our bit pattern, which is just the number of bits in it. And 0 is going to be the rightmost bit, or the least significant, right? So we'll start with a bit pattern that looks like this. And what we're going to use is for the formula for a binary base 2 unsigned integer, given a bit vector like this, we can plug and play this formula, right? So let's work through this. So one of the things we might do is identify, well, what are our actual indexed values? So what is W in this case? Well, W is going to be 4, right? We have 4 bits here. So what is B index 0? That's going to be this value here, 0. What is B index 1? That's going to be the second digit here, 1. B index 2 is going to be this one. And B index 3 is going to be 0, right? This last 0 here, right? So we're counting our indices up from the low order, or the least significant digit, all the way up to the most significant, right? And then we have our summation, right? So our summation is w minus 1, so w is 4, so 3, and our variable that we're counting is 0, so I starts from 0, and our formula is b of I, which is this bit vector, so each index that we wrote out, those will be plugged in there, multiply by, and this is the important piece here. In fact, I'm going to highlight it in a different color so that we can draw some attention to it. In the base 10 system, we used 10 to the I here. In the base 2 system, we're increasing each placeholder's value by a power of 2, so we're going to multiply it or scale it by 2 raised to the placeholder index, right? So in the 1's position, we're going to multiply it by 1. In the 2's position, we would multiply it by 2 to the first, or 2, and so on. So let's actually expand this out and get a feel for it. All right. So the expansion here is going to be, let's think from 0. So b0 multiplied by 2 to the 0. That's one term. We're summing, so the summation, the next term is going to be b to the 1, or sorry, b subscript 1 multiplied by 2 to the 1. And then we're looking for the bit vectors index 2 multiplied by 2 squared. And we're going to add that on to the bit vector's third bit multiplied by 2 to the third. All right. So let's simplify this or plug in our value. So b0 is 0. 0 multiplied by 2 to the 0. It doesn't actually matter. That's going to be 0, but let's be explicit here. B to the 1 is 1 multiplied by 2 to the 1 is 2, right? And we could have gone ahead and let's simplify this. 0 times 1 for the first placeholder value. This is the 1's place. This was the 2's place, right? Let's keep moving. Plus b index 2, that's 1, multiplied by 2 squared, so 4, right? So we have the 1's place, the 2's place, the 4's place, and notice each placeholder in a binary number is doubling in its placeholder's scaling factor rather than increasing by an order of 10 in decimal. And similarly, last but not least, our most significant digit is b index 3, right? That's this digit here. Well, in this case, we've got a 0, so this will ultimately cancel out. It won't mean anything. But 2 to the 3 would be 8, right? So if there was a 1 there, we would be multiplying it by 8. So we can scale this, or we can simplify this a little bit further. 0 plus 2 plus 4 plus 0, right? And this ultimately simplifies to 6, right? And so if we were to go back and look at our representation of when we were counting up by 1s, were we counting up in the correct way? Was this equal to 6? And sure enough, it would be. So the same idea applies that you're fundamentally trying to use with decimals and giving values to certain placeholders in binary, where we're giving each place an increasing magnitude of a power of 2. So the 1's place, 2's place, 4's place, 8, 16, 32, 64, 128, 256, and so on. And the more comfortable and the more time you spend in a digital world, the more comfortable you'll get with base 2 with the powers of 2, right? What I want to stress upon you is that the same intuitions that you know and love about the decimal system apply directly here. That knowledge transfers. The only difference is the number of characters you have available in your digit set, right? Previously we had 10, here we have 2. Next we'll look at what happens if we had 16 and why might that be valuable. And it turns out we use base 16 or hexadecimal all the time in digital computation. And there's a close relationship between base 16 and a nibble or 4 bits. And I think you can probably make that connection. How many different combinations can you form? And if base 16, there are 16 different digits, that means we can represent one nibble with 1 digit of hexadecimal, and we'll look at that next. For reference purposes on the slide deck, you will see that there's the example we just worked through fully worked out if you want to go back through that in your own time. Great work.